Hello everyone. My name is Afrin Maliyat, and today, with my groupmates Abdul Aziz and Siddhant Kotian, we are going to present our project named Design and Simulation of a Hybrid Energy System for Ramea Island. Our project supervisor is Dr. Tariq Iqbal. The table of content of our project includes the introduction, literature review, Ramea Island, information, its electrical power system, it's our proposed system design, and the Homer simulation results. Our dynamic modeling was done in MATLAB. Its calculations and results and analyses are shown in this presentation, and also the conclusion. So we know that the use of renewable energy systems is widespread due to their declining cost and rising efficiency. Renewable energy is defined as energy produced from environmentally friendly, clean sources. Our project examines the design, optimal sizing, and control of hybrid power system to replace the current wind diesel system of Ramey Island. The project focuses on developing a hybrid power system for Ramey Island, which is located in Newfoundland, Canada. Ramea Island now has a wind diesel power plant. However, the wind turbines are not operational. So in our project, we have designed a hybrid energy system for the island, which includes solar-powered PV panels, new wind turbines, battery storage, and a diesel generator. We did a thorough literature review for our project. So these are the papers that we looked into, and we looked into few of the papers, like the first paper, which was by Abul Hosseini. We saw that the advantages of wind power is very high. So it is very clean source of energy, and it is the least expensive renewable energy available today. We have looked into a lot of papers, and we have looked into papers which included hybrid power systems or hybrid energy systems. For example, we have looked into the paper that was published by Dr. Tariq Iqbal and Payne and Paul. It showed the primary design and feasibility analysis of a hybrid system for St. Brendan's, Newfoundland. There's also another paper of Dr. Tariq Iqbal, which discussed the fundamental design of hybrid energy system in or around the area of St. John's. The paper concluded that wind turbine-based energy system with battery storage was most suitable for the places around St. John's, and it also stated that the PV addition makes a small contribution to the energy grid and might not be practical in this region of Canada. We also have looked into another paper published by Rohimul, MD Asif, Hassan, and Dr. Tariq Iqbal. It examines the viability of a pumped hydro storage system in place of existing electrolyzer and hydrogen generator system, and proposes a new way of simulating energy power plant or power system in Ramea Island, Newfoundland. So where is this Ramea Island? So Ramea is a very small community in Newfoundland and Labrador, Canada. It is located on the northwest island of the 5 major islands of the south coast of the province. The island is about 3.14 kilometers long and 0.93 kilometers broad. Ramea currently has a population of 388 people living in 206 of its 207 total private homes. And currently it has a...
So now we will speak on Ramea Island power system. Looking into the current system arrangement, this data was acquired from NL Hydro. So currently there are the Ramea Island distribution load is fed through 3 diesel generators, which are of 925 kilowatts, and the make is Caterpillar. And there are also 3 wind power turbines which were installed by NL Hydro and which are currently not operational. There is also an independent power operator called Frontier Power Systems, who has installed three 65 kilowatt wind turbines. And moving on to the, we can see the diagrams here. We can see the Ramea diesel plant power system arrangement, and these are the three diesel generators. And the middle flow chart, we can see the fuel consumption. Diagram shows the wind power turbines arrangement. And moving on to the proposed system design, before concluding on a final design, the system design was analyzed in RE-Opt, RET Screen, and Homer Pro, which are like the renewable integration and optimizing platforms. Out of these, the Homer Pro gave us the best optimized and feasible design in terms of renewable energy. So our proposed schematic system design consists of solar power panels, solar powered PV panels, and we have a diesel generator of 500 kilowatts, and this is our daily load energy requirement, which is up to 9195 kilowatt hour per day. And we have 100 kilowatt northern power wind turbines, and we have an inverter of 680 kilowatts, and also we have batteries which upon optimization gives us like we will be using 1924 kilowatts rating of power panels, solar panels. And we have also the batteries which are with a string size of 60 and 148 strings which are connected in parallel, and the bus voltage is set to 720 volts. So, and moving on to the Homer simulation results, here we can see that the predominantly the wind turbines are providing the power, and the second stands the solar panels, and a minor part of power load is also shared by the diesel generator, which is only like 0.296 percentage, and 79.3 percentage is the load which is fed through the wind turbines, and 20.4 percentage is the load fed from the solar panels. And here we can see the annual power production distribution, how it is, like which source is feeding how much amount of load. And here we can see the total cost, levelized cost of energy, which is like $0.29, and this is the operating cost, which includes maintenance and undefined costs, and also the renewable fraction. Because this is an hybrid system, we can see the renewable fraction is we are acquiring it up to 99.1 percentage. And moving on to the cash flow analysis, here we can see the initial capital cost, and this plot is for a period of 25 years, and at the end of 25 years, this is what it shows, like how much amount of money is returned back in value.
I am Siddhant, and I'll be explaining you the dynamic modeling in MATLAB using Simulink for our project. So we are having three main power sources in this simulation, which is going to be the PV array, the wind turbine, and the diesel generator. In the PV array system, we have first the PV module. In the PV array, the same specifications of the string and as in series and parallel with the rated outputs have been given as specified by Aziz in the previous slides. And the irradiance given to this is the constant irradiance and the constant temperature which is taken for the site, which is 15 degrees, and the standard average irradiance throughout the entire year. This output of the PV array is then given to the DC to DC buck converter circuit, which you are seeing next. The calculations of this entire circuit, which is the DC to DC buck converter, will be explained in the further slides. And let me explain what this is supposed to do. As a PV array's voltage may not be stable due to it being a renewable source and it depending on the solar irradiation. So a DC to DC buck converter is required to maintain the stable voltage for the DC bus, which we have selected at 720 volt. So the DC to by using this DC to DC buck converter, the voltage will be maintained as 720 volt, which will be supplied to the battery, which is connected at 720 volts. And here you can see a diode which is also placed here, which is going to act as a blocking diode, reverse blocking diode, such that in any case of shadings or during night time, the battery does not give a reverse current back to the PV array. And the main control for this PV system to get the maximum output is given by the MPPT control, which we have designed right up here. This is our MPPT control for the PV array, which follows the P and O algorithm for the MPPT. And next, coming to the second renewable source, which is our wind turbine. The wind turbines are supplied by constants of constant pitch angle and per unit speeds are kept as constant, as well as the wind speed. For this simulation, we have taken the average wind speed for the point of for throughout the year. So next, this wind turbine is a standalone turbine which is giving its parameter or stock parameters to the generator. This generator in turn will provide you the three-phase output, which is in AC, three-phase AC output, which is then given to a two-level converter. This two-level converter then converts it back into a DC form, which is again converted using a DC to DC converter to maintain the 720 volts given to the DC bus voltage. So this converter here is basically used to keep it at 720 volts, and the main renewable source, which are both connected to the systems, are first given to the battery source, and from there they would be taken to the universal bridge rectifier to supply to the load. This is because renewable sources would not be a stable source of energy at all points of time, as they are very dependent on the natural resources at all points of time. So sending them through a battery system is the most reliable way of implementing the system. Next, now coming to the diesel generator. As the diesel generator is a reliable source, it does not need to go through the battery system. It is connected to a three-phase breaker to the AC bus, which is going to be supplying the load. So right now, while you're looking at the loads, we are having two load blocks here. To simulate the changes in the loads in dynamic modeling, we are having these two loads, where one of the loads will always be connected and the other load will be switched on and off to show the difference in the dynamic reaction of the system. So this can be given through the three-phase breakers, which are given to the system, where in the first three-phase breaker will be on throughout, and in the second three-phase breaker to the second load will be switching on and off to show the dynamic differences in the load. Now, all of this can be noticed through the graphs generated by the scope 1 here, which is going to be on the load side, and the scope here, which is going to be taking the values from the battery. These are the calculations which are required to calculate the PV array, the DC buck converter, and the MPPT logic. So as seen, these are the calculations which you can use. Even the DC to DC buck converter, where we need the output current, the inductance, and the capacitance used for the circuit. And here the MPPT logic, where it takes the measurement of the output of the solar panel, which is the voltage and current, calculates the power, and measures the difference of the power. So if there is a difference in power, it would appropriately increase or decrease the voltage to obtain the maximum power extraction. Coming to the outputs of the scopes, checking the load values here, we can see that the load voltage is constant throughout the system, despite there being a change in the load. So as you observe here, the part over here, the first segment, is operating on a partial load, and even the segment here is operating on the partial load, while the segment in between here is operating on full load. So this graph here, the second graph here, shows how the power changes throughout the simulation as a load is being added and removed. When it's operating from a specified load to the peak load condition right over here in this, and coming back to a lower load. But despite the changes in load, we are having a constant voltage throughout the system. Next, in the same thing, here is the graphical representation of that of the batteries, where the initial state of charge of the batteries is at 50, and to supply the demand, the battery is even steadily discharging into the system. Next, coming into the current of the battery, when the system is operating on the partial load, we have a certain amount of current, but as soon as you see the load, when it starts operating at the full load conditions, there is a spike in the amount of current drawn, representing the time at which the full load current is drawn. And here, when you are coming to the voltage, there is a constant voltage here, as we have designed it for the constant voltage.
Thank you, Siddhant. So now let's come to the conclusion of our project. So for the project, we have examined a hybrid power system for Ramea Island, and our hybrid system included solar panels, wind turbines, diesel generators with battery banks, and inverter to produce electricity for the island. In our project, at first we did Homer simulation, which wind turbine or solar panel or diesel generator to use, and the Homer gave us the optimized results. After Homer simulation, a dynamic simulation of the hybrid system was done in MATLAB Simulink. The dynamic modeling consisted of solar panels which used maximum power point tracking for extracting maximum power from the sun. And we had permanent magnet synchronous generator wind turbines, and to extract the maximum wind energy from the wind turbines. As renewable energy resources are not always reliable and they keep on fluctuating, a backup diesel generator was implemented in our project. The diesel generator would supply the AC load with power when we don't have the renewable resources available. The system's dynamic modeling allowed us to fully comprehend how the system functions in different modes and settings. This is what our project included. There is also further scope for a project for improvement. And thank you, everyone. I hope you liked our project, and thank you.